Hi, welcome to another video from Game Theory course, and in this one we are going to discuss games with pure continuous strategies. So last time we already discussed mixed strategies, which can be also considered as an example of continuous strategies. So as for today, we are going to concentrate on pure continuous strategies. So the games with no mixing. Okay, so as you remember, we applied best response analysis in order to solve games with simultaneous moves and rollback analysis in order to solve games with sequential moves. And both of these methods are based on comparing payoffs associated with combination of different strategies. So it makes sense only as long as we deal with a relatively small number of strategies. So in this case, you can just compare and figure out which one is associated with the best possible payoff. However, if we deal with big or even infinitely big number of possible strategies, this approach starts to be kind of questionable. So this means that we will need to use another technique, and this technique is payoff function optimization. Okay, so we are going to discuss the procedure of solving games with pure continuous strategies based on the Cournot duopoly example. So this is a kind of a canonical example. And assumptions are as follows. There are two firms selling homogeneous good, or more informally, they are selling identical good, and they decide on the quantity they are going to supply under complete strategic uncertainty. So this implies that the strategies we are going to analyze are going to be related to the quantities, yeah? Because as you remember, strategy is a complete set of actions, and in this case, possible actions are related to quantities. And as we discussed during the very first lecture, strategic uncertainty refers to the condition when players have no information about moves which were or are made by other players during the previous rounds of the game. So we discussed these games as games with simultaneous moves, but this is rather informal notation. Decisions can be postponed in time, it's fine, but only as long as players do not have information about moves made by other players. We assume that market demand function defines market price for each level of the joint supply. So quantity demanded is equal to A, which is some constant, minus P, which is market price. We assume that the market is cleared, so quantity demanded is equal to quantity supplied by two firms, like it's equal to total supply. Total supply is equal to supply of the first firm plus supply of the second firm. And we also assume that marginal costs are constant and identical, just for the sake of simplicity. So C1, marginal cost for the first firm, is equal to C2, marginal cost for the second firm, and they are both equal to C. Also it will imply that average total cost is a linear function, but again, it's not crucial here. Okay, so as you remember, one of the key assumptions of game theory is that perfectly rational players attempt to achieve best possible payoff. And for firms, obviously, such a payoff takes the form of their profit. This means that in order to figure out how rational firm will act, first we need to define profit function. Okay, I'm just going to discuss the algebra behind this very briefly. So this is market demand function, and we can define inverse demand function, like saying informally how price depends on quantity, in this manner. So if QD is equal to A minus P, then P is equal to A minus QD. But we also remember that the market is cleared, so Q is equal to QD. That's why we can replace quantity demanded with Q. And again, as you remember, Q stands for the total supply of the first and the second firm. That's why we can replace Q with the sum of Q1 and Q2. So market price is equal to A minus, in brackets, Q1 plus Q2. Profit function, profit in general can be calculated as the difference between total revenue and total cost. Total revenue is calculated as the product of price and quantity. So for the first firm, total revenue is calculated as Q1 times market price minus total cost, again the product of C1 and Q1. For the second firm, profit is calculated as Q2 times market price minus CQ times Q2. Okay, again, as you remember, one of the key assumptions of game theory is strategic interdependence of the players, which means that your strategy is going to affect not only your payoff, but also payoffs of other players, and vice versa. Strategies implemented by other players are going to affect their payoff and your payoff as well. So when you take a look at profit functions of the first and the second firm, you can easily detect these elements of strategic interdependence. So the profit of the first firm is affected by quantity produced and sold by the first firm, and it's also affected by the quantity produced and sold by the second firm, and the opposite. Okay, so at the final step, we replace C1 and C2 with C, because as you remember, we assumed that marginal costs are constant and equal, and here they are. So we have profit functions. Okay, so in order to maximize profit, we need to apply first order condition, which literally says that in order to find the extreme point of function, you need to find marginal function and equalize it to 0. Of course, in this case, we calculate, no, it's fine. So, of course, in this case, we calculate partial derivative because any profit, both pi1 and pi2, is the function of q1 and q2. But analyze it from this perspective. The first firm can control only quantity produced by this first firm. That's why we can only calculate partial derivative with respect to Q1. In this case, Q2 is treated as some exogenous constraint we just take as given and we have no control over. Of course, the first firm has no control over. So that's why we calculate partial derivative of pi1 with respect to Q1. It gives you A minus 2Q1 minus Q2 minus C, and we equalize it to 0. Of course, there is no guarantee that this extreme point will correspond to maximum. That's why, in order to make sure that point we are looking for is indeed maximum of the function, not minimum, we have to apply second order condition and calculate the second derivative of this function, like derivative of the derivative. So from this you will get negative 2, which is less than 0, negative, obviously. And this means that the point we are looking for is indeed maximum of the function, not minimum. Because second order condition states that if second derivative is negative, it's maximum. If it's positive, it's minimum. And basically we are done. Of course, solution will be very similar in case of the second firm. Again, we apply first order condition. In this case, we calculate partial derivative of pi2 with respect to q2. And then we apply second order condition in order to verify that we indeed look for maximum of this function. Okay, so the next step is to derive best response function. So we take this expression we obtained from first order condition, and we need to solve it for Q1. So we need to express Q1 as the function of exogenous variables A and C and quantity produced by the second firm. And this function will literally tell you how many units the first firm should produce constrained to any quantity produced by the second firm in order to maximize its profit. So it's like best response of the first firm depending on the quantity produced by the second firm. Analogously, we calculate best response function for the second firm. Of course, in this case, we detect optimal quantity produced by the second firm depending on any quantity produced by the first firm. Okay, so here you can see visualization of best response functions. Here we have Q1 on the horizontal axis and Q2 on vertical axis. So it's relatively easy to depict this function when it comes to the second firm, because here you have Q2 expressed as the dependent variable, and then the intercept of this function will be equal to a minus c over 2, and the slope of this function will be equal to negative 1 over 2, as you can see here. But you can also apply some simple algebra and detect the value of vertical and horizontal intercept when it comes to best response function of the first firm. Okay, and on the intercept of two best response functions, we have Nash equilibrium. Again, you need to recall the definition of Nash equilibrium. I will do it for you. So Nash equilibrium occurs when two players pursue their optimal strategies simultaneously and being aware that other firms do the same. Other players do the same. In our case, of course, firms. So again, best response function stands for the optimal profit maximizing response depending on the to any strategy implemented by the second player, the other player to be more precise. So when two firms pursue their best strategies simultaneously, being aware that other firm will do the same, by definition we have Nash equilibrium. Okay, so if we know that Nash equilibrium is defined by the intercept of best response function of the first firm and best response function of the second firm, then we can relatively easily calculate quantities corresponding to Nash equilibrium. And in order to do this, we just need to solve a system of equations. So in this case, we deal with two best response functions of the first and the second firm respectively. Here we are. In this case, of course, we can replace Q2 from best response function of the first firm and Q1 from the best response function of the second firm with optimal values, because again, this is a kind of an equilibrium condition. We assume that both firms are rational and they are mutually aware about rationality of other player. And then it's relatively easy, so there are only technical issues. You need to put the function corresponding to Q2 to the equation of Q1. This is what you are going to get. You make some relatively simple transformations, and then you get 4Q1 optimal is equal to A minus C plus Q1 optimal. And then you just simplify everything and calculate the optimal value of Q1, which will be equal to A minus C over 3. Then you put this value to the best response function of the second firm, and what you get is A minus C over 3. And congratulations, we are done. Okay, so before we proceed to some other examples, I would just briefly summarize the algorithm of solving games under pure continuous strategies. So first, you have to define payoff function not necessarily profit function, just the payoff function, which of course will depend on the strategy implemented by the first player and other players. Then we need to apply first order condition and maximize this function with respect to variable under player's control. So as I said, the first firm can only control quantity produced by the first firm. That's why we are going to maximize pi1 with respect to q1, and analogously we are going to maximize pi2 with respect to q2. Then you need to derive best response functions. So how strategy optimal strategy to be implemented by each player will depend on strategies implemented by other players. And then you just need to use the notion of Nash equilibrium and find the values corresponding to the intercept of two best response functions. So we've done it here, and here we are. So this is the solution of this game, or Nash equilibrium. Okay, so just to practice, let's do another example. And this is example from Dixit textbook. Monica and Nancy have formed a business partnership to provide consulting services in the golf industry. Okay, sorry, it's just very funny to read something like this during the pandemic. They each have to decide how much effort to put into the business. Let M be the amount of effort put into the business by Monica, and N the amount of effort put in by Nancy. The joint profits of the partnership are given by the following function: 4M plus 4N plus MN, which makes sense because profit of the business will depend positively on effort, in tens of thousands of dollars, and the two partners split these profits equally. However, they must each separately incur the costs of their own effort. The cost to Monica of her effort is M squared, while the cost to Nancy of her effort is N squared, both measured in tens of thousands of dollars. Each partner must make her effort decision without knowing what effort decision the other player has made. Again, we deal under strategic uncertainty, which is perfectly fine for applying this notion of simultaneous games with pure continuous strategies. So, question A. If Monica and Nancy each put in effort of one, which corresponds to $10,000, then what are their payoffs? Again, if you'd like to practice, you can put this video on hold and I will just proceed with the solution. So the first thing you have to do is to calculate, derive, define, whatever, payoff function for both players. So in case of Monica, it's going to be profit split by 2, because half of profit is going to each player, minus M squared. In case of Nancy, again, profit divided by 2 minus N squared. Then you have just put 1 instead of M and N. So you will get 4 times 1, which gives you 4, plus 4 times 1, which gives you 4, plus 1 times 1, which gives you 1, minus 1 squared. So for both players, because they have symmetrical payoff function and in this task they make the same amount of effort, the payoff is going to be equal to 3.5 because we measure everything in thousands of dollars, $35,000. Okay, so this one is relatively easy. If Monica puts in her effort of M equal to 1, then what is Nancy's best response? So this one is a bit more complicated. But because we have already defined a payoff function for Nancy, so in this case we have to put 1 instead of M, because Nancy knows that Monica is going to pay 1 or 10,000 of effort, whatever you prefer. So if you do this, then her payoff function is calculated as 2 plus 2n plus n over 2 minus n. So if you wonder how I got this, this is just some simple linear transformation of Nancy's payoff function here, where I put when I put 1 instead of m, because we know that Monica is going to make 1 unit of effort. So here we have it, and so in this case it's the function of one variable, because we know that Monica is going to pay 1 unit of effort. That's why it makes no sense to analyze it with respect to m. We already know that m is equal to 1. And by applying first order condition, this is what we get. So if you find the derivative of this function and you equalize it to 1, and from this we have 2.5n minus n squared equal to 0. Okay, so probably I said equalize it to 1. Of course, I meant equalize it to 0, because first order condition says that you have to find marginal function and equalize it to 0. So if you do this, you have 2.5n minus n squared. The derivative is equal to 2.5 minus 2n equal to 0. And when you rearrange it, this is what you're going to have. So if you solve this extremely simple linear equation, you will get optimal amount of effort made by Nancy equal to 1.25. So if Monica makes 1 unit of effort or 10,000 of effort, then Nancy should make 1.25 units or 12.5 thousand of effort. So finally, in point C, we have to find equilibrium. And as you remember, the idea of equilibrium in pure continuous strategies games is that we detect equilibrium by calculating the values of variables corresponding to strategies on the intercept of two best response functions. So now you will have to calculate derivative of Monica's payoff function and Nancy's payoff function, define their best response functions. So for Monica, m as the function of n, for Nancy, n as the function of m, and define the values corresponding to intercept of those functions. And here is the solution. So in case of Monica, we have to find partial derivative of her payoff function with respect to m. Of course, n here, because m is the variable under Monica's control, equalize it to 0. So this is what we are going to get. Again, you just have to calculate partial derivative of this function with respect to m and equalize it to 0. And I assume here we are. So m is going to be equal to 1 plus n over 4. Again, you can apply second order condition and find derivative of this function. You will get -2, which proves that Monica's payoff is going to be maximized, not minimized. You do the very same operation for Nancy, but it's relatively easy because their profit functions are symmetrical. So you can verify it, but I believe this time there is no mistake. So n is going to be equal to 1 plus m over 4. And probably it's a bit misleading because there should be an arrow here. Okay, now it's more readable. So this is the function of equations to be solved. This is Monica's payoff function. M is equal to 1 plus n over 4. And this is Nancy's payoff function. I just rearranged it to have m as the function of n. So this is just the same. You can apply a set of linear transformations and get this function out. Why cannot I just highlight it? Okay, this second function out of this function. I just put it in this way because then it's relatively easy to draw, yeah? So you see that the value of intercept is going to be equal to -4, and the slope of this function is equal to 4. So just based on this logic. But of course, you might not do this if you do not have to. if you do not want to. I just feel that it's relatively easy to draw the functions in this manner. I mean linear functions. Okay, so this is Nancy's function. If n is equal to 0, then m is equal to -4. This is Monica's function. If n is equal to 0, m is equal to 1, and the slope of this function is 1/4. And on the intercept of two functions, we have Nash equilibrium, which again means that two rational players pursue their optimal strategies simultaneously, being aware that other rational players do exactly the same. And if you solve this set of equations, you are going to detect that the optimal amount of effort to be made by Nancy and Monica is equal to 1.33. Okay, so that was it. Thank you for your attention.